Maintaining the so-called cloud isn't just invisible magic. It requires a massive, heavy industrial footprint of steel, concrete, and silicon. AWS built a global grid of 123 availability zones in 39 regions, lashed together by 9 million kilometers of fiber. This distributed system assumes failure, instantly rerouting traffic around compromised nodes to maintain constant service. By placing 123 data centers within reach of nearly every major market, AWS has built a physical infrastructure layer that allows businesses to scale computing power without the delays of traditional hardware procurement. To understand why this massive grid exists, we have to look back at the limitations of early 2000s computing. At that time, traditional on-premises infrastructure was slow and monolithic. Under the old model, companies had to forecast traffic, purchase physical servers in advance, wait for hardware shipping, and handle manual installation. It often took months before a single line of code reached a user. This logistical density reflects the extreme scaling pressures Amazon faced as a retail giant. By 2003, hypergrowth turned their internal infrastructure into a restrictive bottleneck. Talented engineering teams were spending their time managing the foundational muck of servers and storage, instead of writing code that improved the customer experience. To survive their own success, Amazon realized they had to separate the hardware procurement process from the software development cycle. The solution began with a 2003 internal paper that proposed modularizing and standardizing Amazon's infrastructure into separate, independent services. This is Cape Town, South Africa. It was here, thousands of miles from Seattle, that a small team began building the core compute platform. That geographic distance shielded the project from being overmanaged during its formative stages. They established a new model, infrastructure as a service. This relies on virtualization. A software layer called a hypervisor abstracts a single piece of physical hardware into multiple programmable virtual servers, known as EC2 instances. You manage the physical capacity entirely through code. AWS launched this model publicly with the Simple Queue service in 2004, followed by S3 and EC2 in 2006. This shift to an operational expenditure model meant developers could rent virtual capacity instantly, like a utility, paying only for the resources they consumed. Renting a single virtual instance is only the first step. Because hardware inevitably fails, the architecture of the system must assume and survive that failure. We start by placing those virtual instances inside a base physical unit, a single data center. AWS clusters these facilities into an availability zone, a discrete failure domain with redundant power, cooling, and security. These AZs are grouped into a region, which must consist of at least 3 isolated availability zones, separated by distance, but connected by ultra-low latency networks. Some cloud providers define a region as a single data center. This leaves their customers vulnerable to a localized power outage or natural disaster. AWS's nested redundancy allows for synchronous replication. A data center can go offline without the end user experiencing any loss in performance. To coordinate these regional facility clusters, the network expands into global intercontinental connectivity. AWS operates a transit backbone consisting of over 9 million kilometers of custom terrestrial and subsea fiber. This macro shot shows the literal glass strands that carry global cloud data. The internet runs on these tiny tubes, stretching along the ocean floor. AWS invests directly in these subsea cable corridors globally to ensure route diversity and bypass public internet congestion. When multiple subsea cables were damaged off the Ivory Coast in 2024, AWS's automated tools rerouted 96% of network traffic without human intervention. Owning the physical fiber backbone is a strategic necessity to guarantee the low latency and fault tolerance of the global cloud economy. We follow the data from the deep-sea fiber backbone to the final mile, the edge. Here we encounter the physical limit of latency. Data takes time to travel from a centralized server across the globe to a user. Amazon Route 53 acts as an intelligent DNS switchboard, calculating the fastest physical path for a request while bypassing congested routes. Simultaneously, Amazon CloudFront uses local points of presence to cache static content physically closer to the user. This layered networking stack ensures that globally distributed applications handle millions of requests without lag. Edge architecture pushes compute and storage directly into metropolitan areas, enabling the single millisecond response times modern applications require. Physical hardware and fiber networks are only useful if you build what the market needs. This requires a strict organizational framework. Amazon uses a methodology called working backwards, a cultural principle that drives all of their infrastructure expansion. Before a single line of code is written, product managers must draft a mock press release and a frequently asked questions document. This forces engineering teams to reverse engineer technical solutions directly from a defined customer problem and the desired end result. Traditional engineering models often build products in a vacuum and then search for an audience. This rigid, customer-obsessed constraint ensures product-market fit and prevents AWS from wasting capital on theoretical infrastructure. AWS changed how businesses operate by combining virtualized hardware, a fault-tolerant physical grid, and the working backwards mechanism. The current technological trajectory is moving towards custom silicon and agentic AI. With 9 million kilometers of fiber and custom AI silicon, AWS provides the physical backbone necessary for global digital innovation.